So I would like to ask you to make a short presentation,
Yes,
right? About using Stellar FM. Let's see. Who start first? So I will call the name. I mean from the order of name list. Muhammad Abdel Hafiz-san.
Yes.
Are you here?
Yes, can you hear me?
Okay. Can you make a presentation?
Yes, I will share now.
Yeah.
Can you see my screen now?
Yes.
Okay, so I tried to use Stera 3D to see the value of using FRB sheets on steel member. So this steel member is simplified into this one. We can see I tried to use another software for calculation of moment just to know the most stretched member. We can see that the largest moment here at the middle of the member, the red member. So I worked on this member and I calculated the dimension of this member. So this is a simulation for the loads that should be affected on the middle. So
very nice.
The middle part will be the most stressed part.
It's not Stellar FM.
No, I tried to know which part to use first.
Much better than this.
Okay. So this is the I member, and I modeled it on Stellar 3D.
Yeah.
So I use the boundary condition to be fixed on all from the bottom because the member is attached to composite column here, so it will be fixed condition. Second, I give the properties of steel structure for density and Boltzmann ratio and thickness. I assume that I am working on a strip with 1 meter long. Then I affected the force like this one. Just to affect to see that I have like shear force acting on all the member. After that, I run the calculation and I get this case 0 for no FRB. You can see that the value for stresses from 2.8 to minus 41. Then I try to use different FRB sheets with different these properties, and I wrapped the beam in this way, and we can see that the forces are different because when we add the FRB, the center of mass for the member moves, so we tend to get more stresses. But when I increased the thickness, this is case 1, we can see it runs from 10 to minus 70. It was minimized to be from 4 to minus 44. So I added another, sorry, this was the case 1, sorry. Okay, so I added another stress and another strip, and I increased the thickness of it. Okay, so we can see now that we have 3 colors. The thickness of the green color is 1,500, so that's the length of the strip. So the stress went from minus 44 to minus 41, so it's getting decreased. So at the end, I wrapped all the section of the I-beam in this way, so the stresses were decreased to be minus 22. So I can know now the best way to wrap the I-beam to reduce the stresses acting on it. Okay.
Yeah, it's very practical. Yeah.
Yes. Thank you.
Okay, good. So any question from student participants? No? Okay. So may I move to Shahid Hamza-san. can you make a presentation? I cannot hear your voice.
Oh, okay, yes.
Okay. Now I can hear. Are you sharing your screen? Nothing up here.
Just.
Okay, it's coming. Okay.
Okay, so I was searching about the examples. So my name is Shahid Hamza. I am from Coastal Engineering Laboratory. And my laboratory is coastal engineering, so I try to find the force on the effect on the wall by the tsunami, which is example 5 on the lecture. So I make the model. There are 3 different structure. Like the basic one is concrete, and there are different properties to each structure. So I will explain the properties. So mostly the density of the structure is 2400, which is quite equal to the concrete density, and Poisson ratio is also same as concrete, 0.166. And the third material used is whose density is 1700, which is less than the concrete density, and all the mesh is 1 meter length. The grid size is on the x-axis it is 1 meter, on the y-axis it is also 1 meter.
Shahido-san, so you use 3 elements?
Yes, 3 elements.
And which one is concrete? Blue one or?
Yes, blue one.
Blue one. And light blue in the middle. What is this?
E1 and E2 are it is same.
I mean, you mean both material concrete?
Yes, concrete.
Okay.
And
green one?
The green one is similar type of like brick, you can say, not concrete.
Okay.
It has less density.
Okay.
And the size of the grid is 1 meter along x-axis, y-axis, and along z-axis. So the force is applied hydrostatic pressure according to the water force. For example, the tsunami height is above the surface. If we take the height above the surface of the tsunami and move downwards here, it is considered the height of water which apply the pressure on the structure. So I calculated the forces which applied on every segment by the height of the water surface. So as the water surface height decrease, then the forces acting on this structure is also decreased. So then I run the simulation, and it shows the effect on the structure, and its maximum tension is 6.59 and compression is minus 13.54.
How did you calculate tsunami force?
Tsunami force, it is by the example, it is written that there is a tsunami and whose height is 21 meter.
Uh-huh.
So I just use this formula. Pressure is equal to rho g h,
Okay.
and then change the height according to the example, and then find the forces.
Okay.
So concrete is a stiff material, so that shows little deformation. If we increase the amplitude, then this deformation increase. So the result shows us that the blue area is tension, and the point of acting of force, it is compression. Thank you for the presentation.
Okay. Okay. Good. Okay. May I move to Mohamed Makbul-san?
Thank you,
Mohamed
Sensei.
Makbul-san.
Okay, thank you.
Are you ready?
Yes, Sensei. Can you see this presentation? All of you?
Oh, I can see white screen. Nothing.
Okay.
Just a white screen. Okay.
Okay.
Yeah.
Thank you. Okay, so today I am going to present a presentation on seismic design of structure and advanced structure by using Stera FEM analysis. So I choose the example 4 from the given example which Sensei provided us by email, a concrete block analysis, and what effects occurs on the block when different kind of kung fu and try to broken by a force. So properties of the hollow block is length 390 millimeters and thickness 120 millimeters and height 190 millimeters and modulus of elasticity Nisman and density 14 kilogram per meter cube and Poisson ratio 0.2. So I took this data from the paper which one available on the Google and where these value of hollow block was available. So analysis model I designed on the FEM analysis and their elements I use is only one, and I use pin both end of the bottom of the concrete hollow block and applied 180 kilonewton force in the mid of the model, as when Kung Fu Master and other people try to broken. And the specification of the model is thickness 120 meter, master elastic modulus 12, Poisson ratio 0.2, and density 1400. And pin force which I applied only perpendicular in y direction 180 Newton. And after applying force, I did analysis, and the results which I get is maximum compression is 0.222 kilonewton, and the maximum tension I get, which is showing blue color, is 0.13 kilonewton. Thank you for your attention.
Okay. So I mean, Why did you select this problem?
I search a lot of gear, but there are some typical model related to mechanical. So mechanical design, I'm from the mechanical department, so mechanical design and model is difficult to design here.
Okay.
So here I choose this one because I don't have idea about civil structure. So that's why I choose this them.
Okay. Okay. Good. Okay. So let's move to next person. Zafira-san, are you here? Okay.
Yes, Sensei.
Yeah.
I will share my screen.
Yeah.
Okay. Can everyone see my screen?
Yes.
Okay. So today I will present about a story. It's not sterile with sterile FEM.
Okay. Okay.
Okay.
Okay.
So today presentation is about this structure. This structure is about is named Two Moons. This building in Seoul, Korea. So actually the client request for a very simple building because he have a very low budget and but he wants something that very how to say impeccable design. So the architecture inspired a moon design. If you can see the dot here like a star, this one is like a horoscope. So is the concept is a moon and star. So this building is for like showcase like galleries for public use. So this one it have 3 stories. So if you can see here, they also it rather than concrete concrete wall, it also have beam and column. So they have beam in the middle, and here you can see the column from the plan view 1, 2, 3, and here also 1, 2, 3, and this one is a wall structure. So we also known as a shear wall. Okay, and this one is level 2 in the middle, and the third one is the rooftop, the third level. Okay, so the total area of the building is 598 meters square. So I expect they doesn't have a specific dimension, but I estimate if the height of the one story is 3 meter, so I estimate the radius of the moon is 3 meter. So I calculate the circumference curve is 4.7, and then I calculate the distributed load from the curve to this wall. So it's 1,567 Newton. Okay, and then this is the front view. So this is the input data. The thickness of the wall is 200. Modulus elasticity 40. And the portion ratio is 0.166. And then the density of concrete is 2,500. And then the boundary condition at the bottom is P. And then the force is 1567 Newton. And then this is the FM result. So if you can see here, the building is compressed to this side, and the blue one is a tension, and this one is the compression only here and here, but not so much. And then this one for side view. So I try to analyze them, but I apply the window. So this how it deform, and you can see this. The blue one is tension, and the red one is the compressions, and the green one is in the middle. And then this one for the west side of the building. So the window here, and then this is how it deformed. The difference before and after. Previously, if you see the bottom, the opening here, this is for the window. It doesn't have so much opening, but the west side of the building, the opening is more than half of the building. So if you can see, and the deflections here, it have more deflection compared to previous one. So result, the highest displacement should be this one, the waist side, because it have larger opening, and then the compression and also the compression and the tension stress also, the highest will be the west one because it have a larger opening at the bottom. So this is my presentation. Thank you so much.
Okay. Very good.
Thank
So you said this house is constructed in South Korea.
Yes, in South Korea. It's very
It is
beautiful.
a private house?
It's not house sensei. It's like a gallery for showcase.
Gallery?
Yeah, gallery.
Oh.
Showroom. Yeah. It's also attracting tourists to visit here because a very unique structure.
But it looks left structure and right structure, the size of circle is not the same.
Yes, it's not same sensei.
But from the picture, right side, small picture, it looks the same.
Oh, maybe I can show you in the internet. The two moon. It have more.
Maybe from the direction of viewing, maybe
I think so.
the size maybe a two moon building.
Building. Okay, so if you can see here, okay, they have. Okay, this one look higher.
Oh, yeah.
If we can.
Oh, many
but if
pixels
we
here.
see in the detail here, sensei, I think it's the same height from the front view. Yeah.
But when you look from I don't know which side, but it depends on the look.
Yeah, I believe so.
Where are you watching from?
Yeah, like this.
Like this.
Difference.
I see. Very interesting.
It's very nice.
Very nice.
Cheap and nice.
Okay. Nice work.
Thank you.
Good. Okay, so who is the next? ヘンダンさん Are you ready?
Yes. Excuse me. Is my presentation seen?
Okay.
Well, thank you for these opportunities. I would like to explain about the structured work system of Indonesia traditional houses that consists with the same materials. And I will explain or I will analyze from the pole of the building. From traditional house in Indonesia, but I just put in 3 traditional house of types. First is traditional house of Naga in West Java, and the second is traditional house of Nias in West Sumatra, and the third or the last is the traditional house of Joglo in Yogyakarta. Where I want to analyze about the pole, there are 3 types different models. First, we are compact, and there is a cross pole, and there is a planted pole. First, traditional house of Java. Excuse me, because I'm not from architecture or civil engineering. I just show up the picture of the traditional house models. And where in this picture we can see that the pole from Naga house in West Java, there is that's the poles unseen because after the columns it's a wall by woods. And for the analysis I use by Steraham. this empty side, I just put the whole side by the types, and after I put the reinforced contrast. Excuse me, because I've used the same formula for the three types because I want to see how it impacts or influence for the three types with the same earthquake, with the same shake, and with the same strength. And after I analyze this, I got that in Naga house there is an impact impact for the shake. After this, we can see there is still there will still a crack in the bottom, and there will still a crack in the on the surface. The maximum compression power is 1 minus 0.065, and maximum tensile force is 0.025. And next to the traditional house of West Nias, there is a complicated pole in the type of models because there's an across pole for the traditional house. So when I try to analyze with Stera frame, I little bit shocked because after I use how to the amplitude, if I up and make it down, it's still no movement. So I can get the analysis with this picture because after I analyze, it's still the same. It's still the same models, Sensei. And I
Maybe
use
the element of near the center. This is only one element connecting at the corner only, right? Maybe this element is not appropriate. I mean,
because I tried it again and again, but I still have the same analysis result because if I make it move right here, it's still no straight line or what, and there is if I click this analyzing, it doesn't see any colors.
Okay.
And it's a little bit shocking for me. And when I get to the last traditional houses, where is which is the pole is still same by the first. It's different just the number of the pole. And after I analyze with this same formulates in analysis, there is a shaking movement. After I click this one and one, there is a movement like the first house, but on the second house there is no any result movement, Sensei. That's why I'm shocking. And this is the result of the last house.
Shahido-san, what do you want to say? You have any comment? You raise your hand. Shahido-san, I cannot hear your voice.
Sorry.
Shahido-san, I cannot hear your voice. Okay, Enda-san.
Hello, can you hear me?
Yeah. Yes.
If you don't apply sport on the base, then it will not show any results. In the second example, I think you will you are not applying any base port, so that's why it is.
This the type of the houses for they're in different types to build. For the first and the last traditional house, the pole is planted on the ground, but for the second houses types, the pole is not planted. It just built by how to say, pillar on the ground and stone and the
Stone. For
and
stone you have to apply.
pole. So I think that's the type of structure that makes why traditional house of Nias get stronger than both of the others.
Okay. Well, let's discuss about the problem of the second model. There is no response. Maybe
Yes.
let's discuss later.
Okay, Sensei. Thank
Thank you. So, shall we move to the last person, Andy-san? Handa-san?
Yeah. Thank you, Sensei.
Yeah.
Presentation mic. Do you see my screen?
Yes.
Thank you for the opportunity. I want to explain about entrance gate. I will simulate. I put four models for the entrance gate, and then the element is modulus of elasticity is 23 kilonewton, position 0.16, and density is 2,400 kilogram per meter. Analyzed condition is 1,000. This is a vertical load, and then material is concrete. With the entrance gate is 6 meter and the length is 6 meter. Totally area in white and in the peak is 22.88, and then in this picture is total 19, and then this is I apply in styrofoam, entrance gate 1, entrance gate 2, and entrance gate 3 and 4. This is the result. I put the thickness 2 centimeter, 20 centimeter, and then 40 centimeter, 60 centimeter, and 80 centimeter, and this is the result of this is the tension for entrance gate 1, and then this is the result of the entrance gate entrance 2, and then this is the result of gate entrance 3, and then this is the result of gate entrance 4. I put in here all the result of simulation, and then the first is gate entrance 4, and then gate entrance 2, and then 3 and 1. So the conclusion based on simulation result, the highest gate entrance 1, and the second is entrance 3, and the third is gate entrance 2, and the last is gate entrance 4. And the greater of the thickness make the smaller tension and compression effect. Thank you. That's all for me.
Very good. Good work.
Thank you.
Okay. So I wanna check what happened to Henderson's problem. Let me try. And I will share my screen. see. どうかなどうかなSo I wonder if you have an element, something like this. I don't know if you can get answer or not, because this is only one element connected at the corner. Maybe, I don't know if it works. Let me try. Yeah, it's error message happens. No response. Yeah, because so this element is not how to say good. You must at least need some element. Maybe in this case, I don't know. Maybe Enda-san, what's your opinion?
Excuse me, Sensei, and for my previous, I put the key on the left side. After I try from the upside and left side, it still have the same result. There is no response, Sensei.
Yeah. So you must avoid connecting only at one point here, right? Two elements are connected at the only corner, one point. Maybe this is the reason. It's not good. So, for example, let's see. Let's increase element. 20 by 20. Okay. And okay. So maybe the diagonal element you put some thickness, right? So this time it is not only one element. Okay. So let me try. Maybe I think it works this time. Okay. Okay. That's the example. Okay, and you put fixed basement. Okay, and you apply.
Yes.
Oh no. Apply force horizontally. Okay, let's see. Run. Okay, it's working now. It takes time to draw the color. Wait a moment. But anyway, so if you make a little bit thickness and I mean many elements, maybe it will work.
Yes.
Okay.
Yes, sir.
Oh, okay. So during waiting, it takes time to put the color. I wanna discuss about the. Okay, okay. Now, can you see? Okay. So I want to discuss lecture schedule. Maybe Word file. And today is January 25, 2026. And the next lecture will be 26. Second of February. Yeah. And okay, and 9 and 16. Okay. And this is actually exam, but we don't have exam. This lecture doesn't have any exam. I will how to say, decide the score based on the report or presentation. Okay. So today's presentation is also I check score. Yeah. And lecture, I mean no class, maybe no class. And so today's presentation, right? So I have 2 class more. So I didn't explain the theory of FEM. I want to explain the theory, but it's a little bit boring. So I don't know. If you are interested in, I would like to explain the theory. How about one moment. Let's see. About Muhammad Makbul-san, you belong to mechanical engineering, right?
Yes, sensei.
So I think you are very familiar to finite element method.
Yes, sensei. My final research also on finite analysis and C software.
So you already know the theory,
Yeah.
basic theory.
Yeah.
Okay. Okay, so I will think about to explain something more related to earthquake engineering.
Yeah.
Okay, I don't know if I show this slide or not. I just want to check. One moment. Today my computer is very slow. I don't know why. Yeah. So Andy-san, you are still in Indonesia?
Yes, sensei. I'm still in
Okay. And Zafira-san is still in Malaysia. Well, you know, Omicron is spreading in Japan also. I don't know when it will, finish. Maybe we must live together with Omicron. But I live with my mother. She's 85 years old. So it's very, danger for her to be, infected by the Omicron. So, okay, now I want to show this slide. Let me share my screen. One moment. It takes time. Okay. Okay. I will finish maybe soon. Just I want to. First, I want to check if I show this slide. This is a story about long period ground motion. One moment. Okay. Response spectrum, I believe I explained this response spectrum. So it is a kind of power of earthquake. Horizontal axis is a frequency and period. And the vertical axis is a response acceleration. So, for example, 1995 Kobe earthquake, this graph has a very high power at 0.2 seconds. Yeah? So it means the response of two-story building. Two-story building natural period is 0.1 multiply number of stories. So 0.2 seconds is a short story building. And the response is very large at the moment of Kobe. So in the Kobe city, at that moment, many private house was broken. And more than 6,000 people were killed. Yeah? But in Kobe, there was a high-rise building, but no damage. Why? Because the natural period of the high-rise building is more than 2 seconds. But because this is a more than 20-story building, and the power of earthquake is very small. So it means this earthquake doesn't have component of long period. The Kobe earthquake was a near source earthquake. So it happened just beneath the Kobe city. So it contains very high frequency. So period is very small and high power at 0.2 seconds. Yeah. So, and another building is base isolation building. It is a building with base rubber bearing at the bottom. Okay? The purpose of this putting rubber bearing is movement of building is very slow because there is a rubber at the bottom, and it will elongate natural period. Yeah? So we believe elongation of natural period is very, very important to protect building from earthquake, to avoid resonance. However, most earthquake here, Kobe earthquake, El Centro, Taft, and the most common earthquake has a large power, less than 1 second. Okay? Less than 1 second. But there is earthquake which has a long period component. For example, when Tohoku earthquake happens, building in Tokyo vibrate. Only high-rise building vibrate long time. Can you see the movement? It is 1 meter movement at the top of the building. Okay? But what we are surprised was not this building. The building in Osaka. This building is located 700 kilometers far from epicenter. Very, very far from epicenter. But at the top of the building, it moved 3 meters left and right because of resonance. Okay? And the 3-meter movement is something like this. Can you see this movement continue long time? And this is a video, I mean, TV program. I was young at that time. Anyway. And this movement happens because response spectrum Osaka City is blue one. Okay? It has no power, less than 1 second, but very high power at 6 seconds. Okay? So it's not the same as Kobe El Centro Taft. It is very peculiar earthquake, which is generated in deep sedimentary soil in Osaka, and its slow movement, 6-second period. So that's why 6 seconds means 60-story building, and this building is 57 story, and the sensor at the 52nd story recorded 3-meter movement. Yeah? So the dominant period of earthquake and the building natural period match together, and the resonance happens. So this is the reason of this, large movement. Yeah. So this is the mechanism why long period earthquake happens. So this is a section of Tokyo City. Tokyo City consists of very deep sedimentary soil, yeah, and very soft soil. And the earthquake comes, it will travel on the surface, so it's a surface wave, and reflecting at the one end and coming back, and reflecting again. So it continues long time, and it also travels far distance. So this is a computer simulation of earthquake wave. So it shows the intensity of earthquake wave. Okay? It is spreading, but it continues shaking in Tokyo because it's traveling, and coming back and continue long time on the surface of the sedimentary soil. It is a long period ground motion. Yeah? And this type of soil exists many places in Japan, maybe in your country also. And you can see this is a map of Japan, and the red part is a deep soil, deep sedimentary soil exists. Yeah? It is made by ash from volcano mainly. Yeah? And Tokyo is the largest plain in Japan, and Nagoya, Osaka. So those big cities are located on this sedimentary soil because these places are flat. And Japan is so many mountains, not so many flat places. So we construct buildings and cities in flat places, but those places are, a lot of soft soil. And 2003 off Tokachi earthquake, it happened in Hokkaido, and the damage happened to oil storage tank. And the oil storage, you can see the bottom picture. There's oil in the tank, and the oil is a liquid, it's moving. We call sloshing movement. And it has a period, 7 seconds. And if the oil tank is large size, sometimes it is 10 seconds. Okay? And at the moment of Tokachi earthquake, this sloshing movement happens because the earthquake was a long period, and fire started. So it was actual damage to long period structure. So now we are worrying about the movement of the high-rise building and may have damage. Okay? And also long span bridge. Also, it has a long period. Yeah. So risk of long period structure. So this is a kind of a problem of new building. I mean, because this is not a small building. Small building doesn't have any problem for long period ground motion. But if you have a big structure, high-rise building, long span bridge, many oil storage tank, you must be careful about long period ground motion. So then we started testing to check the safety of high-rise building. And the test was conducted at the E-Defense shaking table. It is the largest shaking table in the world. Yeah. So this is a specimen. So huge, but we cannot construct a high-rise building on shaking table if even shaking table is big. So we construct only bottom part of the high-rise building, 4-story, and the upper part we just put the mass. Yeah? And we also put detail to represent old type of high-rise building, because we worry about not new type, old high-rise building constructed in 1970s, yeah, and made of steel. But the steel is not, welded at a factory. At that time, it was welded by hand. Yeah. But anyway, so and we started shaking table test. Can you see top part is only mass, but it's moving, and the lower part is real size, structure. And as you notice, this earthquake is not rapid; it's slowly movement because long period ground motion, and it continue long time. So now you can hear the noise. It is the noise of fracture of steel element. And the size of shaking table is 15 meter and 20 meter. Very big size shaking table. But anyway, after this test, we found out some damage to beam end, especially welding part. But so we compared welding in the factory and welding in the side at the side by hand. So this graph shows a kind of plastic deformation capacity. So if this value is high, it means it can absorb, it can resist against plastic deformation. So welding in the factory is much better than welding at the side. Also, we examine the damage of inside, non-structural element, partition wall, but not so big damage. Yeah. But anyway, we notice damage may happen at the welding part. So high-rise building in Japan is not safe. Yeah. And then we started another test, high-rise building of reinforced concrete. It is how many? 20-story reinforced concrete. So this time, we didn't test real size. We tested 1/4 scale building. Yeah. And this is a shaking table. Yeah. How do you think? So specimen is a white one. Okay. And there is a steel frame. It is a supporter. So we worry that this specimen may collapse. So in case of collapse, this steel frame will catch and protect the shaking table. So anyway, please look at the movement of white frame. Yeah, let's show you again. So anyway, can you imagine how much deformation happens to this model? Actually, it is very large deformation, and the deformation is concentrated in the middle part, and the story drift angle is 1/37. You know, because the building is designed to be 1/200 under medium earthquake and 1/100 under large earthquake. So 1/37 is over than design, criteria. And I tried to simulate this model by Stella 3D, but I didn't success. Why I didn't success? Because I will show next slide. Can you see? This is a movement inside the building, and as you can see here, floor is reinforced concrete slab. Floor is also moving. I will show you again. It's moving together with beam and column. Right? So we must consider this floor contribution. How we consider this floor in the analysis. So this is not so easy. For example, in Stella 3D or even design code, we consider, orange colored area. I mean, this is a kind of a contribution of floor against the bending of beam. So the shape of the element looks like a T shape. That's why when you run Stella 3D, where's the Stella 3D? When you run Stella 3D, and when you click beam, you can see there's a slab here, but not all the slab. It is like a T-shape slab, right? So how much area you should consider? This is different depending on design code. Usually we consider 20% of beam length, left and right side. But from this simulation, test result, we notice after getting, large deformation like 1/37, slab effect is getting higher. And finally, all floor contribute against bending. So I modified Stella 3D to consider slab effect and the slip behavior. So finally, considering all lengths of contribution. So this is a Stella 3D simulation. Yeah? And I compared with test result. Yeah? So test result is a red one. This is a story drift, left one. And right side is a shear force. Yeah? And the white blue is a previous analysis by Stella 3D. I couldn't success. Yeah? And also shear force was small. Then I consider slab effect more, full total area. So the solid blue line is, modified Stella 3D model. It's getting better. Yeah? So my learning is Stella 3D is not perfect. So always we must compare with test results. Okay, and the high-rise building is affected by long period ground motion. Yeah. Okay, so and we installed passive damper to reduce movement against long period earthquake. So recently, this is the example putting many damper in the middle part of the building. So originally, this building was not constructed in 1979, but no damper inside. So in case of long period ground motion, it will may have damage. So they decided to put 288 oil damper. Oil damper is, there is a steel brace, V shape, and the bottom part, there is a small oil damper. Even small, it can, I think, how much? 100 kilonewton power. And you can bring this damper by elevator. So it's not so difficult to bring this damper. Okay? And even new building has many damper inside. So this is a high-rise building with viscous damper, also steel damper, mixed together in the building. It is a 21-story building. And this is a 41-story building. It is also damper number is 688. So it is a new building. So, designed initially with damper. So many damper inside. And if you want to put damper, to existing building, there are many ways. One way is to put some frame, and the damper is a brace part, okay? Or how to say, or a damper is a horizontal arrangement. So arrangement of damper, depends on the designer. Also, sometimes, if you put the brace type, people complain, oh, there is a brace in my window. If you are living there, it's annoying. So in this case, sometimes we put some column type damper. So damper is at the center, and it's not a brace; it's like a column. But the column type actually not so effective. Stiffness is not so high compared to brace. But for the people who live inside the building, column type is not so annoying. You can watch outside without interruption by the brace. Okay? And if you put damper in the high-rise building, another thing you must be careful is, if you arrange damper vertically, and if you have earthquake horizontally, one side is tension, the other side is compression. Yeah? So this kind of overturning moment, tension and compression force will happen because of damper. Damper, if you continuously arrange, it is like one shear wall, continuous shear wall. So it will behave like a cantilever. Okay? So tension side and compression side, happens. And you must be careful to the design of compression side and tension side. Yeah. Maybe column will be broken by compression failure. Buckling may happen. Okay? So this kind of problem you must be careful. Okay? So brace type damper produce large axial force, and it requires retrofitting of column or a foundation. Okay? Expensive. So changing foundation is very, very expensive. So just putting damper is not so expensive, but if you be careful, this kind of behavior. Okay, maybe that's all today. So I will think about what we will discuss next time. I try to be interesting subject. Prepare. Okay, so is it okay to finish?
Okay,
See you next week. Yeah. Bye bye.
Thank you, Sensei.
Bye bye.